Hi class, in today's video we're going to be talking about section 2.9, inverse functions. And so remember back when we were thinking about functions, we had something called the vertical line test. And what did we use the vertical line test for? Well, if we had a graph of a function, whatever that might look like, something like that, as long as there was no point where when we drew a vertical line, it intersected twice, and so this one seems to, except for right there, maybe. I didn't mean for it to, so we'll just erase that. Right, as long as it went no vertical line past it twice, it was a function. So the vertical line test determined if a graph was a function. And what did that vertical line test show us? It showed us that for a given x value, there was only one y value. A given x value went to one y value, right? Because if we had, for example, this graph that looked like that, if we would draw a vertical line now, let's say that's at x equals 2, x equals 2 corresponds both to a positive 3 and a negative 2. And when we drew our set model for our function, every x value had to go to only one y value. And so we're going to consider a related idea today, and that's the idea of a 1-to-1 function. So a function, each x had only one y value, but two x values could have had the same y value. For example, if we graph our friend the absolute value, both -1 and 1, right? Both -1 and 1, f of -1 equals f of 1 equaled 1, right? So a function, two x values can have the same y value. But we have a special name for functions where each y value has only one corresponding x value. And these are called 1-to-1 functions. And so we can think of it as each y value has only one corresponding x value. In other words, and this is our formal definition, if different elements of the domain of f, are assigned different y values, then the function is 1-to-1. 1-to-1. So let me draw you a picture. And now this will be similar to that squiggly graph I drew before. So here, suppose we look at this point and this point and say that's at 2, 3, 4, 5, and 6, right? They both map to, that's 1, 2, 3, 4. So here f of 2 equals 4 and f of 6 equals 4. So this function is not 1 to 1. And this is called the horizontal. And you may be saying, well, why do we care if a function is 1 to 1? Why do we care if two x values map to the same y value? Well, soon we're going to want to talk about the idea of an inverse. And so we can think of that as inverse of f, a way of undoing. And if our map takes, or if our inverse, let me pick a different color, takes a y value back to an x value, if the same y value goes to 2, the inverse won't say, well, no, if we give it, say, f inverse of 4, well, it won't know, should I spit out a 2 or should I spit out a 6, right? So that's why we care about an inverse, or about 1 to 1. So we'll come to the point that 1 to 1 functions are invertible, meaning they have inverses. In other words, we can undo them. So, other than graphing, right? Because if we graph something and it looks like that, that looks like it passes the horizontal line test. Well, as long as I get rid of that part there, that definitely doesn't look like it does. How can we know if a function is 1 to 1? So testing for 1 to 1 algebraically. So let g of x equal negative 2x plus 5. Well, let x1 and x2 be two elements in the domain of G. That means g of x1 is just negative 2x1 plus 5, and g of x2 equals negative 2x2 plus 5. And what we want to show, if 1 to 1 means that y values have unique inputs, let's suppose g of x1 equals g of x2. And what we want to do is show x1 equals x2. Because if those two correspond to the same x value, that means that it will be 1 to 1. So we have negative 2x1 plus 5 equals negative 2x2 plus 5. Subtract a 5 from both sides. Divide both sides by negative 2. We get x1 equals x2. So if we have two y values that are the same, they must have the same x value. You might be saying, well, when won't this be the case? So if they're equal, we get that it's 1 to 1. But what if they're not? Or when will that even happen? So let f of x equal the square root, actually the negative square root of 9 minus x squared. And so suppose f of x1 equals f of x2. So we have negative square root 9 minus x1 squared equals negative square root 9 minus x2 squared. Divide both sides by negative 1 and square both sides. 9 minus x1 squared equals 9 minus x2 squared. If I subtract a 9 from both sides and divide both sides by negative 1, we get x1 squared equals x2 squared. I take the square root of both sides. I'm going to get x1 equals plus or minus x. Because remember, when we take the square root of a number, we get a plus or minus. And so here, x doesn't necessarily equal x2. It equals plus or minus. And so what would happen is if we would graph this 9 minus x squared out at 3 and negative 3, we're at 0, and at 0, we're at 3. We have a half circle. So that's f of x. And so for a given y value, say suppose y is 0 if y equals 0, x equals plus or minus 3. Or if y equals 1, x equals that value or that value, and so on and so on. So this is not 1 to 1, and therefore we can also see graphically it does not pass the vertical line test. So there are two ways, I'll write this on the next slide, two ways to test 1 to 1. The first is graph and use the horizontal line test. Horizontal line test. And the second is algebraically. And I would hope that you'll be able to use both of those methods, because we care if a function is 1 to 1, so if a function, we'll call that f, is 1 to 1, the inverse function of f, called f negative 1 or f inverse, exists. And our definition for inverse, definition, f inverse of y equals f if and only if f of x equals y. So that says if x's value in the function goes to y, the inverse function's value of y takes us back to x. So let me give you some examples. So find the given inverse values. If f of 2 equals 0, what is f inverse of 0? And if f of 3 equals negative 3, what is f inverse of negative 3? Well, like I said, the inverse takes the x value, or the y value, the y value back to the x. So if my function's graph is at 2, so let me plot these points. I have 2, 0, and I have 3, negative 3. It says if my y value is 0, what is my x value? It's 2. It says if my y value is negative 3, what's my x value? It's 2. And so generally speaking, the domain of f is the range of f inverse, and the range of f is the domain of f. Right? If that takes my process of xy and gives me yx, makes sense that my range would become my domain, or my domain would become my range. And so let's go ahead and work with this notion of inverses a little bit. But first, I'm going to say verify that f of x equals 2 minus 3x and g of x equals 2 minus x over 3 are inverses. So that means go ahead and find, say, f of 2. And this is just to motivate that they are. F of 2 is going to be 2 minus 3 times 2. That's 2 minus 3 times 2 is 6, negative 4. If g is f's inverse, is g f's inverse? Well, if we take g of negative 4, remember our inverse takes a range value, negative 4, and it should give us back x equals 2. Well, let's see what happens. 2 minus a negative 4 over 3 is 2 plus 4 over 3, which is 6 over 3 is 2. So it looks pretty convincing because g took its value and gave us that. But how do we show that? Well, this is where we're going to revisit function composition. So I'm going to say f of x equals 2 minus 3x, and g of x equals 2 minus x over 3. We're going to find f compose g of x and g compose f of x. So here, f compose g means take g and insert it everywhere we have an x. So we have 2 minus 3 times 2 minus x over 3. So if we take that, we get 2 minus, these 3's will cancel, 2 minus x. We distribute that across. 2 minus 2 plus x gives us x back. What happens when we find g compose f? Well, that says take, and I'll pick a different color. It says take this and insert it where there's an x. So we have 2 minus 3x over 3. 2 minus 2 plus 3x over 3. 2 minus 2 is 0. 3 divided by 3 is 1. And we get x. So if f and g are inverses, f compose g of x equals g compose f of x equals x. In other words, f of f inverse of x, or f compose f inverse of x equals x, implies f and f inverse are indeed inverses. And so, why don't we look at those on a graph? So I'll go to a new slide. We had f of x equals 2 minus 3x, and g of x equals 2 minus x over 3. If you don't mind, I'm going to rewrite that as 2/3 minus 1/3 x. We use f of x in this color. So 2 minus 3x means we have our linear function shifted up 2 with a slope of negative 3. 1, 2, 3 over 1. 1, 2, 3 over 1. Over 1. Up 3, left 1. Up 3, left 1. That's our function, our graph of f of x. Let's pick another one. A green for g of x. So now we're up 2/3, so about there. And then we go down 1, right 3. Down 1, 1, 2, 3. Down 1, 1, 2, 3. Down 1, 1, 2, 3. Up 1, left 3. Up 1, left 3. And so how are those two lines related? Well, it turns out that if I would draw the line y equals x, these lines, so inverses, are symmetric about the y-axis. Well, and why is that? Let's look at an example. Because there you were like, meh, I don't really see it. But you don't have to just take my word for it. Y equals square root of x plus 2. X. And we won't call that y, we'll call it f of x. F of x. And we can go as far down as negative 2, negative 1, 2. That's enough. We get 0, 1, and 2. So if I graph this, at negative 2 it's 0, at negative 1 it's 1, at 2 it's 2, and that's my graph of f of x. Now remember, f inverse of some given y value gives me the x back. And these are our y values. So we have our y values here, 0, 1, 2, and f inverse of this gives us the domain value back, negative 2, negative 1, and 2. So our ordered pairs are 0, negative 2, 1, negative 1, and 2, 2. So if I plot those, 0, negative 2, 1, negative 1, 2, 2, that's f inverse of x. And now, if I carefully draw this line in, you can see since this point, -2, 0, and 0, -2, -1, 1, 1, -1, because these swap positions, we really do have that they are symmetric. Are symmetric. And now you might be wondering, well, if that's what that looks like, how can I find its function value, right? In the previous one, you gave me its inverse. And you were like, well, show me that they're inverses. Or if I'm given points, I know I can just swap them. So finding inverses of functions. You can, we have a couple options. You can either calculate the table, and reverse the ordered pairs. You can graph and flip across the line y equals x. This is the case where it's symmetric about y equals x, or you can find it algebraically. And that's what we'll spend the remainder of our class time on today. Finding inverses algebraically. And I'm going to cut it off there because I'm going to run out of room. So suppose, I'm going to write my steps over there. F of x equals 1 over x minus 1. Our first step is replace f of x with y. So we get y equals 1 over x minus 1. Then you swap x and y. X equals 1 over y minus 1. Then we need to solve for y. So go ahead and multiply this up and divide that over. Y minus 1 equals 1 over x. Add 1 to both sides, 1 over x plus 1. And then 4, replace y with f inverse of x. F inverse of x equals over x plus 1. And now remember, we can check, so let me copy these over. F of x equals 1 over x minus 1. F inverse of x equals, what did I say it equaled? 1 over x plus 1. 1 over x plus 1. And we should have f compose f inverse of x equaling x. So that's 1 over x plus 1 minus 1. Those 1's cancel. 1 over x. Multiply top and bottom by x. We get x. But we don't want to just stop at 1. Is it true that f inverse compose f of x is x? Well, now we have 1 over x minus 1 plus 1. That was taking f and substituting into f inverse. Well, we can multiply by x minus 1, x minus 1, x minus 1 over 1 plus 1. X minus 1 plus 1 is x. Good. So this process does work. Let's try it with another example. F of x equals x minus 1 over x minus 3. And we'll specify that x doesn't equal 3 because then our function is undefined. And on that note, here on our previous example, x doesn't equal 1, otherwise our function is undefined. And so our steps are replace f of x with y, 2 swap x and y, solve for y, and then 4 we replace y with f inverse of x. So we have y equals x minus 1 over x minus 3. Swap x and y, x equals y minus 1 over y minus 3. Multiply y minus 3 over x, y minus 3 equals y minus 1. Distribute x, y minus 3, x equals y minus 1. Get y on its side by itself, x, y minus y equals 3x minus 1. Factor out a y, x minus 1 equals 3x minus 1. Y equals 3x minus 1 over x minus 1. So f inverse of x equals 3x minus 1 over x minus 1. And you know we won't stop there, we'll confirm it. So we have 3x minus 1 over x minus 1, 3x minus 1 over x minus 1. So my claim is f inverse. And f of x we started with was x minus 1 over x minus 3. So f compose f inverse of x equals x minus 1. Not just x though, we have to substitute f inverse. I'll pick a different color. 3x minus 1 over x minus 1 over 3x minus 1 over x minus 1 minus 3. So we're going to need to get a common denominator in both the numerator and the denominator. So with 3x minus 1 is x minus 1 over x minus 1. 3x minus 1 over x minus 1. So we have 3 minus x, let me go back. So we have 3x minus 1 minus x minus 1, so minus x plus 1 over x minus 1, all over 3x minus 1 minus 3x plus 3 over x minus 1. And here what we'll do, we have our x minus 1, so we'll multiply the top and the bottom by the reciprocal of the denominator, x minus 1, 3x minus 1 minus 3x plus 3. And that will cancel that. When I'm running out of room, x minus 1s will cancel. 3x minus 1 minus x plus 1 over 3x minus 1 minus 3x plus 3. Negative 1 and plus 1 cancel. 3x minus x is 2x. 3x minus 3x cancel. Negative 1 plus 3 is 2. 2x over 2 is x. F compose, F inverse of x equals x. Check. And I'll leave you to confirm F inverse compose F of X equals X. So the big takeaways are only 1-to-1 functions have inverses. Inverse functions take range values as inputs and return domain values of our original function, and we can find them with tables, graphs, or algebraically. Our definition is that F inverse of Y equals X if and only F of X equals Y, right? It takes the range value and returns the domain value that provided that. And it returns the corresponding domain value. They're symmetric about the line Y equals X, and we can find them algebraically by swapping X and Y and solving for Y. And that concludes this section. Have a great day, everyone.